And I'm here to talk to you today about why we built VPC and came out of EC2 Classic, how we built it, some of the underlying challenges in the physical networking layer and what that maps into in the virtual networking layer, and how this all translates into a broader platform that we've built with a $0 cost. So I'm going to give the folks in the back coming in just a minute to take a seat. I believe that they have the right to a full session. We will not be hosting Q&A today, but if there are questions, please feel free to come to us afterwards. So in AWS, we have this notion of the cloud. And in the cloud, as in any other traditional on-prem facility, you need a network. If that network is virtual or physical, it doesn't matter. You need a network. And in our cloud, we have services that offer private endpoint connectivity. Private endpoint connectivity means I have an IP address that I can only get to privately. RFC 1918, that would be the 10/8, 172.12, 192.168.16, those private, non-routable, non-advertised address spaces. And in this private endpoint space, you see EC2 for virtual machines. You see Elastic Load Balancing, or ELB, for load balancing of those EC2 virtual machines. We also have private storage, and although that does not have a private endpoint space, it does attach to private virtual machines that do have a private endpoint address space. And of course, Relational Database Service, or RDS, and Redshift. So we have a cloud that offers a number of services that live in a private endpoint space and will take on, generally speaking, non-RFC, RFC 1918 address space. Okay, just for clarification too, we do have a public endpoint space for services like EC2 that do exist in the non-RFC 1918 space so that you can hit them publicly if your security groups allow. But we've got this network. And of course, our customers have data centers. You saw it today in Andy's keynote with VMware on stage. There is a movement from the enterprise and other businesses to come into AWS, and cloud doesn't happen overnight. On the whiteboard, it does. Super easy for us to visualize what does it take to integrate my private data center with Amazon's cloud. We simply draw the data center on the left, we draw the AWS cloud on the right. PowerPoint engineering, it's my favorite. Unfortunately, it's not that easy, right? Because you're going to have address space that you're already provisioned in your on-prem data centers, and you're going to have this networking address space that you've got to integrate. How many in the audience have actually worked for companies that have actually acquired other companies? Yes, more than half. So this is a challenge of integrating two different IP address spaces, is it not? Yeah. This is the first problem that we faced in AWS. More specifically, this is a big problem we faced at Amazon, the actual retailer behind AWS. In our own business, we lived in private data centers for years. That means we have physical facilities that have physical networking. There may be a virtual networking layer or two in there. But how do you transition that to Amazon Web Services? Doesn't happen overnight. Doesn't happen overnight for us. We understand in our customers it won't happen overnight. It's not easy. More on that in a minute. When we started EC2, we started what is now known as EC2 Classic. The idea of one flat network address space that is a 10/8. And the earliest days, it was easy. It allowed us to get the virtual machine service up and running. You could fire a virtual machine up. You would get some random IP address. Here we're seeing 1044.12.4. You fire another one up, your customer orange, your 1044.92.17. You don't know if that's 1044/16. Could be 1044.12/ I'd have to do the CIDR math here. I don't know if I'm in the same CIDR block or not, but I got an IP address. So minimum viable for us allowed the virtual machine service years ago to come up and say, okay, I got IP connectivity. The challenge was other customers, customer blue here comes up next to you and, well, now you're 1044.12.5. What's the challenge here? I've got another customer with an IP address that's a /32 offset from me. They're next door. So no concept of contiguity, contiguous IP address blocks here. This is our challenge in EC2 Classic. Then another customer comes up and he's in the .12 subnet. The point here is that what we know today as EC2 Classic does not work. And why it doesn't work is because if you have a network in your on-prem data center, and I promise you, if you're an enterprise, you're going to be bigger than a 16-bit network, all right? But just to model and keep it simple, let's say you've got 192.168/16 in your on-prem. Your routing table says all local routes have destination here in the on-prem. That's good. The developer fires up that EC2 instance back in the day, the CR1XL, for example, and it comes up 1044.12.4. Developer in an office on corp network that comes back into the on-prem network of 192.168.16 says, I need to SSH into this instance. Let's assume it's a Linux instance. So Mr. Networking Engineer says, all right, I'll create a route destination for you. I'm going to say that all traffic destination 1044.12.4 will route to AWS. Developer's happy. He or she gets to SSH into that instance. Network engineering not so happy. They had to take a trouble ticket, but nonetheless, developer's happy, and that's all that matters. Now another customer comes up, 1044.12.5 next door. That's not you, but you, developer says, I need another instance. They've got this cool service called ELB. 1044.92.17 comes up, and the developer says, now I need to SSH to this one as well. I haven't figured out auto-scaling yet. I haven't figured out CloudFormation, so I'm going to go in there by hand and build it. I need to SSH in as well. So the networking engineer says, I'll give you another /32 route. And over time, what ends up happening is you've got a myriad of destination routes going into your route tables. How many think the network engineer is happy at this point? Both with the developer and with us. Let's be very clear. Right? And the challenge ends up being that as you provision instances, you have to go into the route tables. And as you delete instances, because, right, virtual machines are commodities, you probably should also delete those route table rules. Don't want to orphan that out. Oh, now the network engineer is very upset. Right? Now, what happens if the on-prem goes to 1044/16 and the data center range is different? Unknown. So, singular route destinations to AWS back in the day for EC2 Classic, or what is now known as EC2 Classic, caused a great amount of operational burden on our developers, more specifically our networking engineers. So we said, let's step back and find a way to give every customer the private network that they've come to know in on-prem. This is the evolution of how we move from EC2 Classic into VPC, and the motivation as to why. We needed to make this look more like a traditional physical network, but we're going to do it virtually. So the requirements on this was the customer needs to be able to define their CIDR blocks. If you're in a 1044/16 address space and you want to look like a 1045/16 address space in AWS, you totally can. You get to define the CIDR block in AWS as is. That is the inherent property of VPC. The singular /32 destination routes that the network engineer had to deal with, that's nonsense. That's a recipe for disaster from security perspective and an operational burden, let alone if you have thousands of routes. I'm not sure the router, does it handle it at scale? So we need to aggregate all of the destination traffic to AWS and give you a way to simply say this /16 address or smaller has destination to AWS, or multiple /whatever network's destination to AWS. We need to be able to aggregate all these routes so you don't have singular destination routes. And finally, we said, okay, most importantly for the success of not only VPC, but of AWS, we've got to conform to existing network designs. We have to be able to play into what you, the customer, knows today. We can't tell you what the right way to do is. This is networking. This has been around for 20, 30 years. We have to conform with what exists today. So we went to the whiteboard, we drew out the on-prem box, we drew out the AWS cloud, we put the arrow in, we're done, right? No. What we did is we said, okay, we're going to bring in a new network. It's going to be called Virtual Private Cloud. VPC for short. I say it shorthanded so many times that I have to actually stop and think about the acronym. And if you've been in AWS at any time, you as well will. But what did we do? We said, okay, let's go back to that whiteboard. The on-prem is 192.168/16. Those routes are going to stay here. They're going to route local. They don't need to egress anywhere else. Now, developers want to look at AWS, or maybe we're making a strategic migration, whatever the case may be. Your networking team, or maybe possibly your developers inadvertently, right, have selected 172.31/16 as their network in AWS. So VPC allows us to actually define, for the first time ever, a private network. Now, this is not a novel concept. VPC has been around since 2009, ballpark, 7 years. But we're going back in time to see why we did this and how we did it and the underlying challenges we faced. And so we said, all right, we need to now give you a way to integrate your network of 192.168 with 172.31. And we did this by way of edge points. The visuals here are what you might see as a VGW and a CGW. All right? This implies potentially VPN. It also could apply a different type of edge of direct connect. In this case, with a lock, we indicate VPN. But we have to have some physical networking capability to integrate the two. If we're going to give you this, we're going to bring you in, we need to let you integrate via VPN or possibly circuit integration known as direct connect. More on that later. And as we bring you into the on-prem, now that you've got your own private network, you get your own subnets. So now you get to carve out with VPC back in the day a network that might look like yours with the customer IP address you want, with the range you want that fits into your existing design. This is what we worked towards as we evolved EC2 and realized that private networking was so important. And of course, we went to multiple subnets, and now we can do things like, hey, EC2, I want to map one subnet to AZ1 and one subnet to AZ2, and I want to load balance across those, and I get built-in active-active redundancy. This is the basis for enabling the other services. Now, keep in mind that VPC is private to you and only you. Your network is not shared with another customer's network, and it's actually not even shared with another network in your own account. It is quite possible in the VPC model that we've designed to allow for you to clone that VPC, and I use the word clone with quotes around it. You can create one or more VPCs next to it with the same address block. Now, just side note here, why would we do that? There's value to developers in having VPCs that look the same if they're doing QA environments, dev regression test, etc. All right? But the capability is there. And of course, as your developers spin up instances, or your infrastructure people do, depending on what the workload is, you see that you get to place your EC2 instance into those subnets. Now also keep in mind that we allow you to statically assign private IP address. We allow you to take an IP address via DHCP, which is serviced from VPC behind the scenes as part of the virtual network underneath. Or you can obviously assign a public IP out of our public IP pool, either ephemeral or elastic. And of course, this is just virtual networking. So for the first 15 minutes, you might be looking at me saying, you've just gone backwards in time. Why did we do this? Well, the reason is because we want to help you understand how we built VPC to scale. So in our world, a subnet, if we think about the physical layer here, we have to talk about our terminology in virtual translated to what you'll know in physical. Physical, a VLAN translates in our world to a subnet, okay? A VPC translates to a VRF, so you can have multiple VRFs in your account or multiple VPCs. But what happens if we say that a subnet is a VLAN and a VPC is a VRF? That's great for one customer. It might be great for 4,000 customers, right? What do we do with 1 million customers? Okay, now here's the real engineering. Here's the challenge we have to face in our data centers, in the physical networking layer, in our virtual networking layer. If we said that a VLAN is a subnet, and by VLAN definition you get 4096 theoretical, 12-bit in size, how do we get more than 4,000 subnets? We had to figure that out. And if we said that a VPC is a VRF, how do we have any type of large commercial router that does anything more than a few thousand VRFs? How do we scale this out? Let's back up. If we say that publicly we have over 1 million customers in AWS, and if we assume that all 1 million customers at least have one VPC, how many VRFs are we talking about here? 1 million. We had to look at the hardware. What commercial hardware do we bring in to do this back in the day? We have to map that physical infrastructure to virtual. And of course, there's only a fixed ratio of VLANs to VRFs, and networking engineers don't like a large number of VLANs. So back in that physical layer, you have a big router. Go out and get any of the commercial routers. I won't name names, but you can just imagine the big ones that will cook you dinner and probably make you breakfast. Large, take up lots of rack space. They have a data plane. They have a smaller control plane. That control plane is driven by a traditional CPU with software that you know. Networking gear is the same as any traditional server, physical server. It's just got a different hardware interface. And we say, all right, there is this control plane to data plane interaction through a small bandwidth pipe. Now these data planes, by the way, networking companies really go extra lengths to make these data planes perform very well, right? You want to move megabits, gigabits, terabits through. Data planes got to perform. So custom ASICs, all the hardware all the majors are doing this. And then you want to pair it up, because when that one big router fails, you want to go to the second one in the HA pair. And then of course you've got HA communication between the two. And you're putting a lot of stress on these routers. And so we have this challenge of how do we get a lot of VRFs? And by the way, if we say 1 million today, what does it look like in 5 years? We don't know. Right? We just don't. So we have to scale linearly. And we had to look at how do we do this in a way where we're not having to buy large hardware off commercial banks to do this at a way we can get the price to zero. That's the challenge, right? How do we keep the price zero for you? How do we drive that price to a place that is feasible for you? Let's give you an example of some of the challenges we faced as we looked into the details. So let's say an average router configuration is about 50 characters in size. Let's say for us to configure up a VPC in that physical network layer, it's 10 lines. Say there's 4 subnets on average, 2 public, 2 private, just 4, okay? Let's say a config per subnet is 5. We're now into 20 across the 4. And if we are looking at trying to scale 2,000 VPCs for our customer base, that average config file for the router is 3 megs. So it turns out that in our testing in the labs, as we built VPC out years ago, that file of 3 megabytes took 5 minutes to parse. Let's put this in perspective. You click on the AWS console, you expect your change to be immediate so that routes take effect like that. How do we do it at 2,000 VPCs if it's going to take 5 minutes? How do we go to 1 million? Right? How do we do 1 billion packets? So we needed commodity hardware that we controlled. The big routers we're talking about are built by a handful of commercial companies. Some of these advanced features that get you the size and scale you need are only a few in size or offered by a few. And the interoperability between the companies, because you want to diversify, right, potentially. Blast radius considerations, if I bring big routers in, I want to do a couple different companies. The interoperability diminishes significantly as you go up in advanced feature sets. So let's step back here a bit and talk about capacity. We've talked about how many VPCs we're trying to design for, how this translates into the routers that have to process the configuration files to take effect. Now let's talk in terms of EC2. Let's say I have an HA pair on the left, and I have an HA pair on the right. The pair on the left gets me about 40 EC2 instances, and the pair on the right gets me about 40 EC2 instances. That means I can put I have 40 EC2 instances tied to one router pair and 40 to another. Now, customer A says, all right, well, we're going to come online with 3 EC2 instances, and we allocate into the cap pool of 40. We've got 37 left. We have 3 slotted in there. And the second thing is customer B comes in and says, well, I only need 2. I'm a small company. I'm testing things out. Customer C comes in. We load balance them into the router pair on the left. They've got 4 instances on and on and on. And customer D brings in more virtual machines until customer A says, you know what? Business is expanding. We like AWS. We want more. And as we horizontally scale here, customer E comes online. He's like, I'm just trying it out. And so these customers keep bringing virtual machines in, and the problem we have is we have a placement problem. Your virtual machine is going to go into a router pair and be tied to that, but we only have a physical capacity for so much. And by the way, we don't know your growth. In fact, when G comes online, they blow out the router capacity. But I still have slots for 25 more virtual machines. That's not effective, right? We're spending money on physical hardware, but we're not getting the utilization on the router pair that we want. And what happens when company B goes in and says, all right, we want to be in the VPC on the router pair on the right, and we've now run out of capacity. We've now taken the virtual machine capacity pool on that router pair to 40. What do? We've run out of space in our VPC. This is the challenge of how we have to have a VPC mapping to a router pair with the EC2 instances coming into it, right? So what we said is, from an implementation perspective, we need to scale to millions. And our customer needs to be Amazon.com. It's the only customer we need to focus on. James said it last night. We design our routers for one customer only, Amazon. Any server, anywhere in a region, can host the instance attached to any subnet of VPC. The capacity model you just saw with the HA pair says, hey, I'm going to be able to host any instance in any VPC. But I also need to be able to restrict which instances you're getting to. You got to be able to only get in those VPCs that you own and are part of. So from a concept perspective, how do we do this? So yes, we have Amazon. Amazon has data centers. And yes, we have physical hosts in those. Those physical hosts are our hypervisors. They've identified here in white with server IP addresses of 0.3, 0.4, etc. Those are physical IPs on the physical network in our data center. So we're talking about hypervisors running the EC2 virtual machines that take on physical IP addresses. Now, what we're looking at is how do you put a virtual machine on those hypervisors. Are you going to be on the physical network, or are you going to be on that virtual network? Virtual network. And that's what we're showing here, how it works. EC2 instance blue comes in, customer blue, sorry, comes in with 10.0.0.2. Gets placed on hypervisor 192.168.0.3. 2 more instances come online to 2 different hypervisors with a .1.3 and a .1.4. Hopefully these are in a different AZ, right? So now, more customers come online. Notice that I've got the same IP address being used between customers green, blue, and gray. Earlier I said that VPCs were private to you and your account, that you could have multiple VPCs with the same CIDR block. They would be isolated away from each other. 2 customers and 2 different accounts could have VPCs with the same CIDR block and, again, be isolated from each other. The virtual networking layer we're building here on top of these physical hosts has to accommodate this fact. I have a virtual IP of 10.0.0.2. I'm customer blue. Customer green is on the same host with me, and also 10.0.0.2. So how do we actually ensure that blue gets to blue-only virtual machines and green only gets to green? The answer is in a mapping service. This is the heart and soul of VPC. If you've not seen this, this will explain how we actually get layer 2 and layer 3 Ethernet destination routes to each virtual machine and how that translates back to subnets. So what happens is the mapping service is a distributed lookup, all right? It will map the VPC of an EC2 instance to the physical server that it's on, the physical host. I'm going to be very specific, host here, hypervisor, all right? So let's take a look. Layer 2, I've got an EC2 instance in subnet A that needs to get to another EC2 instance also in subnet A. That's layer 2. How do we do it? Well, from the basics of Ethernet, 10.0.0.2 goes to its switch. It does an ARP. It says, hey, who's got 10.0.0.3? The switch responds with a flood and says, oh, the ARP request out there, 10.0.0.3 is on my switch. I've got it. 10.0.0.3 responds. acts the request, 02 knows where it is, and now it can talk directly to 10.03. That is a physical network. In VPC, the virtual network, the mapping service acts as that element between the origination and the destination. What happens is 10.002 dumps out on the operating system and says, hey, I need to get to 10.003. I'm going to ARP that request. It dumps it, though, to the physical host. We don't want to change the operating system, right? Same drivers, same everything. You import VMs. Whatever you do, you shouldn't be doing any network fun inside the OS. You should delegate down to the hypervisor or lower. And that's what we do. Server, the host, the hypervisor with 192.168.0.3 turns to the mapping service and says, hey, I've got an ARP request out here for 10.003 for customer blue. Where is it? That is the map. And the map says, hold on, I acknowledge he's actually on the host in the bottom right, 168.14. So the mapping service knows that customer blue 10.002 on host 0.3 is trying to get to customer blue 0.3 on host 1.4, and he tells them exactly how to get there on the physical network. So what we're watching is the VPC, or the virtual network, dump its request into the physical network, and the mapping service resolves the two. 10.002 says, thank you very much, and now I can actually issue my layer 2 request again. I want to talk to this other virtual machine in the same subnet. I'm going to send it a packet, and we're going to actually encapsulate the packet. We're going to send the request, and then we're going to encapsulate with information specific to the VPC, along with source and destination rules for the physical network, and host 0.3 sends this encapsulated packet over to host 1.4. Host 1.4 is going to unencapsulate that, de-encapsulate. Now, he's not just going to accept the request, though. That would be too easy, right? There has to be some verification. We have to watch out for the potential of crosstalk between two VPCs. The host is going to turn back to the mapping service and say, hey, I just got a request from physical host 0.3 for a virtual machine running on there for customer blue. Are we good? Is the source good? And the mapping service is going to say, yep. And the request is going to go through. The host will allow that traffic. That is how we perform VPC isolation. Now, take a look at customer Gray's 10.004. He wants to get to 10.003. I don't see a 10.003 out here. Do you guys? Which 10.003 do you see? Right, it's Gray. So the mapping service says, nope, sorry, denied. This prevents crosstalk. This is what allows for VPC isolation. The mapping service handles the source request, tells it where the destination is. The communication goes through the physical layer, and then the destination says, hold on, before I accept that request, let me turn back to the mapping service. And if it's good, if source is verified, then we'll allow the traffic through. Again, if we have 10.004 dump its traffic to 0.4, and he wants to go destination blue, if we play this out, 0.4 isn't hosting any blue instances, and the mapping service again denies. If we assume somehow that a valid mapping was attempted, we could try to use it. So packets cannot and will not flow unless all parties involved, source, destination, and mapping service, agree on where those interfaces are. And as we play this out, physical host 1.4 is going to turn back to the mapping service and say, hold on, I'm getting requests from Gray on that host over there. Am I good? Mapping service raises an alarm and says, sorry, that's invalid. Again, VPC isolation through the source, destination, ACK process on the mapping service. And again, if this occurs, an alarm is raised internally on us. Now, that's assuming two virtual machines want to talk in the same subnet. How do we get from a virtual machine in one subnet to a virtual machine in another subnet? This is layer 3. This is general IP routing. In this scenario, 0.2 virtual machine has to talk to the Ethernet switch and ARPs out and says, hey, I'm trying to get to 0.1.3, but first, where's my gateway? 0.1 is the gateway. Ethernet switch identifies that. Says, awesome. Let's get that to the gateway. Gateway takes it and says, all right, destination request for 1.3. It comes back. That is what we do. Source goes through a gateway to get to the destination. Let's model that in VPC now. I've got a virtual machine in subnet 1, needs to get to virtual machine in subnet 2. In layer 2, when we're all in the same subnet, we just go to the mapping service and back and then directly to the host. It's pretty directly coupled, right? We want a virtual machine to jump from one subnet to another now. He says, hey, I need to get to some instance, but first I need to identify where my gateway is. I got to tell the gateway where I'm going. He says, all right, your gateway is here. The mapping service delivers back not the address of the destination, but the address of the gateway. Comes back to the instance. The instance then dumps the request to the physical host, who goes to the map, and the map comes back and says, okay, I know where you're at. I'm going to create the packet. I'm going to encapsulate the VPC information. We're going to then encapsulate further the physical host information, and we're going to send that directly. So there's a layer of indirection here for layer 3. We have to go to the map first. We have to find the gateway. Then we have to go to the destination. Similar concepts everywhere else. Packet encapsulation for VPC. That encapsulation includes the VPC information, so we can actually say, is this a valid source or not? It also includes the physical host information, so we know how to operate on the physical network in the data center. Again, though, you got to come from the right source. You have to be valid. So the host turns to the mapping service and says, once again, is this a valid request? It's customer blue. I'm allowed. We're good. And there we go. That is how VPC fundamentally works in the layer between virtual networking to physical networking for virtual machines talking in the same subnets and virtual machines wanting to talk in different subnets in the same VPC. Layer 2 is in the same subnet. Layer 3 is in 2 different subnets. Now, all of this has to happen in real time, right? I'm very slow presenting this, but you can't have it operate that slow. This needs to be instantaneous, 0 latency. We're talking about a single packet that's got to get through, multiplied by a factor of 1 billion or more. How do we make this fast? 0 latency is the goal. The answer is caching. We can't continually hit the map service in real time, right? It's not a real-time service. It's a distributed service. Might be millisecond response times, but we need near 0. The answer is that we build cache pools on the physical hosts from the mapping service. Imagine the idea of us decentralizing the map service with the rules that are specific to that host. We're only going to give you the information on the host that makes sense. And why is that? Oops, sorry. Why is that? Because when I'm on a host and I need to get to the destination, the cache should only know about the areas I can get to. It guarantees a 100% hit rate in the cache. I'm not throwing 70% success. Look, there's no gray on the host at 0.3, right? We all can see that? I don't have any gray virtual machines. The cache has no knowledge of gray virtual machines. It only has knowledge of blue and green, because that's every single request that goes through that cache needs to be a 100% hit rate. And that is how we get 0 latency on VPC. All right? And what this allows us to do, if we kind of back up, is we started this with a very flat network in EC2, right? And then we said we need to break this up, we need to privatize the network, we need to give you the capability of private network endpoints, full control over your networking between your on-prem and AWS, and it allows for this. Virtual machines can come up with fixed or DHCP-based addresses, multiple subnets. You get to map those subnets to the availability zones. Virtual machine running at 10.007, getting to 10.009 in the same subnet, does a layer 2 request in the virtual networking layer, known as VPC. And through the mapping service to you, it's transparent. It was real time, but what you really did is went through the cache, which was coming back from the mapping service with a source destination verification on it. If you want to get to another subnet, this is how it all plays out. You're doing a layer 3 request to the destination through the gateway with the same source destination verification. There is this idea of I need to egress traffic out some edge. That edge is a way for me to get somewhere, be it what we call a virtual private gateway or VGW. whose destination is some other network, some physical, or maybe an IGW. So if we expand this further and get outside of what we're doing in the VPC and getting into another network, we find that we actually go through edges and we encapsulate the packets the same way. We say, here's the actual virtual networking information, encapsulated with the VPC information, encapsulated with the physical network information, and have some type of edge allow me to egress traffic. So when you're tunneling packets through that VPN tunnel, destination to your VGW, with the customer gateway, the CGW, on the other side, what you're really doing is going through an edge. And the same holds true for IGW, the internet gateway, as well as Direct Connect, or DX for short. And the way the edge works in VPC is it's the same setup. The physical hypervisor hosts have map caches, the mapping services in place. The virtual network says, hey, listen, I'm on physical host 0.4. I need to get to, I've got a virtual machine on me that needs to get to also 0.4. And I'm going to go to a destination of 172.16/16. That's like my on-prem. So I've got a virtual machine that wants to route traffic to the on-prem. The edge, that VGW internally, looks just like another physical host to us. In this case, it's 4.3. So we send the traffic down to the physical host. We encapsulate it with the virtual networking information, the VPC information, and the physical network information. We send it to the edge, and the traffic egresses. Now, as I mentioned earlier, there are three types of edges. There's a VPN-based edge, or what we call a virtual private gateway, or VGW for short. Packet encapsulated information goes to this 4.3 edge. You know what the edge does? Its job is to translate Amazon proprietary information about VPC to stuff that the real world understands. In this case, with this edge, it's translating to IPsec specific information for the VPN tunnel. So we do packet encapsulation and strip out the VPC information. We do not egress Amazon's network with proprietary VPC information. We put it back on the physical networks in the world, encapsulated with the information specific to them. Case in point, if we look at Direct Connect, this is a circuit. This is us going to a Direct Connect facility, then destination one or more on-prem. We also send requests down to the VGW for Direct Connect, right? You've got your VPC, you want to send traffic to the on-prem, you route it to the VGW. The VGW is really an edge, and the edge's job is to not only look like something local and familiar to you in VPC that we saw in layer 2 and layer 3, but then to also put 802.1q VLAN tag information on it for the real world. So the edge is actually an adapter or a map, if you will. And then finally, the third edge is the internet gateway, or the IGW. This is the border as it lives on Amazon. All right? Same thing. It's just an edge. Its job is to translate between a very proprietary virtual network on our side and a physical world out there, except one difference here. We're not doing IPsec encapsulation. We're not doing VLAN tag encapsulation. What we actually have to do is make it look like you're coming from a public IP. So if you've ever wondered how those elastic IPs work, we take your source information and egress at that point in time with the EIP, or potentially the managed NAT, or the NAT, ephemeral IP but public, or static IP and public. And that is what the edge does at the IGW. Its job is to translate not only the specific information of VPC to the real world, but it also needs to then map into that public IP address so we can talk on the internet. So to recap, VPC not only handles inner subnet traffic and subnet to subnet, but it also has to talk on different destinations. I'm going to egress over VPN. I'm going to egress over Direct Connect. I'm going to egress out the border on AWS via IGW. We have edges in our mapping service to handle all of this, and they look just like any other destination. So, brief diversion. The hardware we built for our routers, so, yeah, okay, the penguin. We talked earlier about physical routers going to scale with us and how that wasn't going to work and how we needed to build commodity hardware that scaled, right? That just looked and felt like a traditional server. And in our world, We built this. The device is known as a Blackfoot, and it's based on Linux, hence the Penguin. Well, it turns out that the Blackfoot Penguin, why they named the device Blackfoot is because Linux, Penguin, the team that did this is based in Cape Town in South Africa. And there's a spot in Cape Town where penguins exist. And the penguin in Cape Town, South Africa, is indigenous to that region, and it's called the Blackfoot. So a little fun fact about Amazon is that, yes, these devices we build are called Blackfoots technically, based on the team in Cape Town who built that in the early days. And we've actually named one of our headquarter buildings. This is the actual photograph of it in Seattle, just outside the South Lake Union campus, known as Blackfoot. And it turns out a lot of product development happens here. So, just wanted to bypass some of the dry networking, get back into a little color on Amazon. So, how much does VPC cost? 0. How much are you guys paying for subnets? Anybody? How much are we upcharging you for your network on an instance? This is the design goal, right? We can't get to 0 if we buy really expensive large commercial hardware. And by the way, it's not that we are adverse to it. It's that you have to scale in ways that they've never had to do, because we have a lot of customers, right? As opposed to a singular customer in a single data center. And so if we buy those at large scale, we're going to pay money, and we have to actually pass that back on, and we don't want to do that. We want to drive price down and make it cost affordable for customers. So, I would bet I get no one who understands what this date is. Anybody have a venture at what this date is? Turns out this is Black Friday for the year 2010. So why is it, when was Black Friday? Last Friday, the 25th? So Amazon.com, Black Friday, what do you think happens for us? Pretty busy, right? What do we decide to do? On November 10th, 2010, we actually shut down the last physical host that ran the retail commerce site, Amazon.com. That's the day we fully went in 100% on retail to EC2. So why is it really important? Because I'm up here talking about VPC and virtual networking, translation to physical networks, egressing on edges, all this stuff, right? Scale. But we're talking about real commerce traffic on Black Friday, just 5-6 years ago. VPC works. If we could survive that, and we've survived Black Fridays, and if this is the last day we've done, then we've done it right. We've built VPC the way it needs to be, at the core. So, just a side note to come back to the Amazon.com story about customer trust in VPC. Broader picture, we talked about lower level things on routing, subnets, etc. VPC itself is a platform, and we can't forget that, right? As a platform, we allow you to build subnets, and those subnets go into private networks known as VPCs. We allow you to egress traffic in and out of those networks with the edges. We now, as a platform, allow you to bring in other private endpoint services. So bringing it back to the start of this session, when we said those relational database services and that Redshift cluster coming in private, the VPC that we talked about ends up creating its own platform, and that platform enables other services. And as a platform, yes, we give you VPN and Direct Connect. We talked about that. But now we build other things on top of it. Hey, I want security groups. Stateful firewalls that do /32 filtering for both inbound and outbound traffic. It gave us the ability to control perimeter traffic with network ACLs at the subnets. Truthfully, most of our customers do security groups because they have longer history than network ACLs, but you have the option to do either one or both. All right? As a platform, VPC gives you the ability to get to routing tables. It gives us the ability to place not only one, but more network interfaces on those EC2 instances, known as elastic network interfaces, right? So as a platform, as we've developed over time, we've been able to get more feature-rich in what we've been able to offer back to the other services. Side note, elastic network interfaces, you get more, you can actually add more based on the instance type if you didn't know that, and yes, you can multi-home them. All right. One of the latest advances in VPC in the past year had been on S3 endpoints. So there's this big movement from our customers who say, hey, VPC, awesome. You guys built it 6, 7 years ago. Thank you very much. We have private endpoint connectivity, but some of your services have a longer history here than EC2. S3 is the one, right? And S3 lives in the public endpoint space. So here's the challenge our customers bring to us. All right, I've got this instance that's private in EC2 in a VPC that needs to talk to S3. I have to get to the internet because S3 is a public endpoint service. Had been, right? Exclusively. And that the engineering on it means if I'm in a private subnet, I have to throw all my traffic through, at the time, NAT instances. Everybody remember NAT instances? How many people were happy to see managed NAT come along? Yeah, it's the whole room, right. I don't even need to ask that question. Yeah, so the challenge is you're literally burning all of this data through NAT instances just to get to S3. It's kind of a waste. Yeah, managed NAT helps you out there, right? The other option was you'd put those instances in a public subnet so you're already on the public endpoint space and you don't have to go through a NAT layer. It's good. The wrong way to do it. So what we did was we said, all right, customers need to make S3 look local. They need to make it look private. There's a big movement, by the way, in the customer base we see with more services that are in the public endpoint space. Customers are asking us to bring them to private endpoint space. So we look at all those requests and we build roadmaps based on customers. So S3 endpoints came. This is private connectivity into S3 from your VPC. Your S3 buckets look local. In our world, they're just another edge. Your virtual machine goes out to S3 through an edge. If I can actually get there. Yep. So we talked about 3 edges earlier. We built a 4th for S3. And if we build more private endpoint connectivity for public endpoint services, like S3, you should expect them to come as edges as well. And they work the same, right? Except this time, we make the edge own the bucket information. So I've got a virtual machine on the virtual network that has a physical server underneath it. It needs to get to S3 as 172.16. That is an edge. And we send the request through the map service. Again, it goes to the physical layer. We encapsulate the packets. And we send it to the edge. So our private endpoint connectivity for S3 goes through an edge, just like Direct Connect, VPN, and Internet Gateway do. This time, we have to encapsulate different. We have to encapsulate with VPC, and we made S3 look like its own VPC endpoint to do it. And we put that information in the green here. So we encapsulate that, and then we encapsulate physical network information. But this time, we're talking public endpoint spaces because S3 is a public endpoint service. So the edge does all the traffic for you locally, makes it look local, and then does the translation as an edge to go to the public endpoint space. We didn't change S3, like we didn't really privatize it. We just built edges to be able to accept source traffic from your VPC and make it look local, so that you didn't have to put NATs, manage NATs, or put your virtual machines in public subnets to get there, right? And then, of course, when we did that, now that we have an edge, we actually introduce a new concept, giving you the ability to secure access to those buckets via policies. So now, with an edge, we've advanced from where we were with Direct Connect, VPN, and IGW, and add an additional layer of security, right? It's an additional layer. And by definition of policy, I can say I'm going to allow access from here to the S3 bucket or deny. In this case, we actually define the resource of the bucket and everything in it. And then we have a policy here that actually says I'm going to go ahead and deny if you're not this source VPC. So the really cool thing here is that the edges got smarter when we did private endpoint connectivity for S3. And you can secure access. That's super important because you may have multiple VPCs in your account and you only want one to access an S3 bucket, right? Prod VPC, Dev VPC, QA VPC. You only want prod traffic going to a prod bucket. That's what we're talking about here, by the way. That's the customer use case. Okay? So in the end, our challenge in building VPC was the simple complex balance. If we go super simple for our customer base, then the most advanced networking engineers won't be happy. Their feature set's limited. But if we go complex, while we satisfy the most hardcore diehard of the network engineers and be flexible for them, those out there who don't really have the CCIEs or don't have the networking expertise are left behind. So what we did is built a flexible model. You can go as simple as you want or as complex as you want. And we allow you to go into full advanced features on VPC or keep it simple with like a default VPC. The default VPC was introduced a few years ago, and its job was to make networking simple. I don't need to think about this. And by the way, there's some type of movement out there we're sensing. I don't know how long the days are where people really need to think about traditional networks. They're here for some time, right? But the question we ask is, do you really need to think about your network? If you can just get somewhere, do you care where you came from, right? So in a default VPC, we spin you up with 172.31/16, and you don't think about it. You provision the instances into the subnets. It's already there. It's if I recall, it's a 2 subnet in the public, 2 subnet in the private, and it allows you to provision, and it makes it feel like EC2 Classic. There was some value to EC2 Classic, by the way, in the fact that I could just provision virtual machines, I get an IP address, and I don't have to think about networking. So default VPC is an attempt to get back there, but keep you in a private endpoint space. And that private endpoint space is, of course, represented here with subnets and the overarching VPC. And it brings in the private connectivity. So where EC2 Classic fell short, default VPC's job is to say, we brought you here, we got you into a private endpoint space, we give you the features you want, but we made it simple for you not to have to worry about so much. Now, I will tell you, most enterprises are not using default VPCs. We understand that. We have to deal with both ends of the spectrum here. Okay? Simple but limited for some, complex for others, but flexible, right? And that is what we're trying to deal with here in VPC. So I realize that people have lines to get to. I'm going to go ahead and recommend some sessions for you. If you've taken a chance to, there's a spelling typo there, count. I recommend the deep dive on Direct Connect and VPN. Netflix's session is also great. If you miss them, be sure to check them on the AWS YouTube channel. Please remember to complete your evaluations. Sorry, for those who are actually taking photos, I'm not going to I got it. So, please be sure to fill out your evaluation. We love customer feedback. I'm going to let everybody take this. Guys, enjoy. Thank you so much.